This video is on titrations and titration curves. A titration is a controlled addition of a titrant used to determine the concentration of an unknown solution. So basically in a titration, we have some titrant, which we know the concentration of, and we have some unknown concentration solution, and we use the amount of one put into the other to figure out the concentration of the thing we don't know. So the titrant goes into the burette, which we'll talk about, and the titrant is the solution of known concentration. Then the analyte is the solution of unknown concentration, and that goes into the Erlenmeyer flask. A weak acid or base that changes colors when the pH changes is called an indicator. And in an indicator, it has a point when it changes colors, and this is known as the endpoint. The equivalence point is different than the endpoint. The equivalence point is when there's equal amounts of hydrogen ions and hydroxide ions. So usually at the point where we get a neutral solution. In a titration, it's to your advantage to have your equivalence point be the same point as your end point. So that way your indicator changes color when you have just over or under a pH of 7. So we'll be doing a titration, and the setup looks like this. You'll have a burette, which is much larger than this, but it's a long cylindrical tube that at the end has a valve to open and shut it, so the liquid in your titrant goes in here, comes and drops down into your analyte. Your analyte, which is your unknown concentration, is in the Erlenmeyer flask, and so that way we know if we've added enough titrant to our analyte, we have an indicator. And the indicator will change colors based on the pH of your solution. This is set up using a ring stand to hold our burette. And when we read a burette, it has the smallest volume is listed at the top of 0 milliliters, and the largest volume, in this case 50 milliliters, is at the bottom. We care about the change in volume that our titrant goes through. So if we started at if we start at 0 milliliters and then we put in enough to get here, that's about 25 milliliters. So I would have added 25 milliliters of titrant to my analyte to figure out the concentration. As we add titrant into our analyte, we can plot our pH of our solution. If we start with an acidic analyte and then add in base, we're going to gradually climb up our pH. My first part here all has a pH under 7, so this is still an acidic solution. At 7, I have a pH that is at my equivalence point, and this should be where my indicator changes. Above 7, I have a basic solution where my pH is above 7. We'll notice that the point of inflection on our titration curve, in this case of a strong acid and a strong base, our point of inflection is where our equivalence point should happen, and this should be at a pH of 7. We can also do calculations to determine how much acid or base we would need to neutralize our solution. When doing these, we can either use stoichiometry or the formula of NMV, where N is the number of moles of water, moles of hydrogen ions or hydroxide ions, and then M is our molarity, which we've learned about before, which is moles per liter. V is our volume. So for my example, what is the concentration of phosphoric acid, H3PO4, if 10 milliliters of acid is neutralized by 20 milliliters of 0.2 molar sodium hydroxide? So I can set up stoichiometry where my given amount is my 20 milliliters of my 0.2 molar sodium hydroxide. So 20 milliliters of sodium hydroxide. And from this, I can figure out my moles. So I'd go from 100 milliliters sodium hydroxide to 1 liter of sodium hydroxide. And I do this because concentration is in moles per liter. This is 0.2 moles per 1 liter. So I go from milliliters to liters. I know that I have 1 liter sodium hydroxide has 0.2 moles of sodium hydroxide in it. So 1 liter sodium hydroxide has 0.20 moles of sodium hydroxide. I use my mole-to-mole ratio to go from moles of sodium hydroxide to moles of phosphoric acid. For every 1 mole of phosphoric acid. And then I know my moles. When I plug this in, I get 0.0013 moles of H3PO4. I can convert moles into liters to find, I can figure out concentration by taking moles divided by the liters that I have. So 10 milliliters is 0.010 liters. So my moles divided by my 0.010 liters gives me a concentration of 0.13 moles per liter. And this is of my phosphoric acid. The same thing can be done using my formula listed here, looking at the moles, concentration, and volume of my acid, A, and my base, B. So my variables are molarity, volume, and my number of moles of either hydrogen for my acid or hydroxides for my base. I have phosphoric acid, sodium hydroxide. What is the concentration of phosphoric acid? That's what I'm looking for. If I have 10 milliliters of acid, neutralized by 20 milliliters of 0.2 molar sodium hydroxide. So my concentration is 0.2 molar, and I have 20 milliliters. I can't forget to do my ends. So the number of hydrogens on my acid is 3, and the number of hydroxides on my base is 1. So I set up my formula, NaMaVa equals NbMbVb. I'm looking for the concentration of my acid, so I plug in 3 times my molarity times my volume of 10 equals 1 times 0.2 times 20. So I want M, so I divide both sides by 3 and 10. So molarity of my acid comes out to be 0.13 moles per liter, which is the same thing I got using my stoichiometry above.